Okay. Good evening everyone. So the last class we talked about linear regression. We derived, we minimized the squared error. We derived the parameters beta naught and beta 1 or whatever you want to call it, alpha, beta, etc. So we derived for univariate or single variable regression, right. We haven't extended it to multivariate, we have done for univariate, and towards the end we ended up with what is known as R square statistic, right. That is the amount of variability explained by the independent variable, right. So how much of x, y is explained by the independent variable x, that is what is R square, right, and if you multiply into percentage 100 it gives you the percentage. The higher it is, the lower the residual variances, and therefore the better the linear fit is. And remember we only purely talked about linear regression, okay. Now if you recall, we fit two parameters, be it alpha, beta or beta naught and beta 1. One is the slope, the other one is directly related to the correlation, the other one is actually what is not captured by correlation, which is the mean value, right. So that is what we had those two parameters to be. Now the next natural step is to look for confidence intervals of these two parameters, right. So anytime a confidence interval includes a 0, that means what, that parameter is essentially 0, right. So if I say my confidence interval is between minus 0.1 to plus 0.1, what does it mean? The confidence interval also includes 0 and therefore that parameter is not present, basically it is 0. So you want to check whether what is the confidence intervals of your parameters, okay, so that it does not include a 0, okay. So for that is what we do. So we can actually derive certain things, okay, I am not going to do it. So this is my beta naught, okay, this is my beta naught or y is equals to alpha plus beta x model, okay. So this is my alpha. So we have, if you remember, if you go back and look at our derivations, okay. So what is your beta naught? Beta naught is y bar minus beta 1 times hat times x bar, right. This is my beta naught, right. And now what is the expected value of beta naught? Is it going to be 0? What is the expected? So this is my expected value of beta naught hat. What is expected value of beta naught hat? This is what I have, okay. Expectation of beta hat is nothing but, which is nothing but expectation of y hat, which is what I have derived here, okay, right. So y bar, yi, this is y bar is nothing but yi by n, okay. So if you take it expectation of beta hat, you take it expectation of y bar, which is, what is y bar and what is yi? I have the model which is nothing but alpha plus beta times xi minus x bar, right. So if you start doing this, you will get what is the value of beta hat to be the original beta, or sorry, this is expectation of alpha hat to be alpha, where y equals to alpha plus beta x plus epsilon, right. So the way I clubbed it inside, right. So you have beta one more term which is y minus beta 1 into xi, right. So that is what I have included here. When I expanded, yi is what actually, yi is truly alpha plus beta x, right. I now introduced beta into xi minus x bar, that is accounted for. So if you want to take it that way, expectation of alpha hat, if I go by that, this is nothing but y bar minus beta times xi. What is y bar? Y bar is nothing but 1 over n times summation yi. What is yi? This is 1 over n, I can take it outside. Yi is nothing but summation also I can take it outside, alpha plus beta xi, and what do I have already here, beta hat times xi. So this is nothing but 1 over n summation alpha plus beta times x minus x, this is x bar actually, this should be this is x bar basically if you look at, okay, xi minus x bar, it is the same term you will get. Okay. So now if you take expectations, it will turn out that expectation of beta naught hat equals to beta naught, this is like expectation of x bar equals to mu, the beta naught hat will boil down to beta naught, which is what this thing, in this case the xi minus x bar will go to 0, 1 over n summation, so it will go to 0, so the first term alone will remain, so there is expectation of alpha hat equals to alpha. You see here basically what is alpha hat, we can clearly derive it from the beginning. Okay, I did not want to derive, I wanted you guys to look at it, but I will derive this alone, I will not derive the other one, I would want you to derive something. Okay. So what is beta naught, we talked about beta naught, so let us keep it at beta naught hat, here beta naught hat equals to alpha hat. Okay, expectation of beta hat equals to what, y bar minus beta 1 hat times x bar. Okay, so what is y bar, y bar is nothing but 1 over n summation yi minus, okay, x bar. Now this is what 1 over n I can take it outside, summation I can, then I have expectation of yi minus x bar, right, what is this term alone, minus y, so 1 over n summation, remember expectation is a linear operator, this is nothing but expectation of what is yi, yi is nothing but alpha or beta naught plus beta 1 xi minus beta 1 x bar, I have expanded on this. Okay, so this is nothing but 1 over n summation, expectation of beta naught is a beta naught, okay, expectation of beta 1 is beta 1, expectation of xi minus beta 1 times x bar. Now what is this, 1 over n summation beta naught, okay, plus what is expectation of xi, x bar beta 1 x bar, so this term gets cancelled. Okay, so this is nothing but 1 over n times n beta naught, which is equals to beta naught, so expectation of beta naught hat equals to beta naught. Okay, the average value of the estimate tends to the truth, that is what this derivation is. And what should be the variance of beta naught hat, this is like average, right, sigma squared over n, you can derive it, I have derived it here. Okay, I have earlier derived this also. Okay, so this is sigma squared over n. Okay, so this is like mean, right, this is mean value is this, so the variance of x bar we know is sigma squared over n. So what is now this this thing going to be, so the variance of alpha hat is also known, expectation of alpha hat is known. Okay, expectation of alpha hat equals to alpha, variance of alpha hat equals to sigma squared over n. So alpha hat follows a normal distribution with alpha comma sigma squared over n, right, the mean value is alpha, the variance is sigma squared over n. Now I can show that with these assumptions, I can show that alpha follows a t distribution with this kind of thing. Okay, so alpha also follows a, or alpha hat or beta beta naught hat follows a t distribution. Typically t will become normal if the number of degrees of freedom are more. Originally alpha hat follows normal distribution, if your number of data points is low, it is going to follow the confidence limit is based on t distribution. okay, and this is sigma square root of MSE by n. Remember our T distribution when we learned T distribution for paired T distribution or single T distribution, we were using sigma square, we were replacing with mean squared error. That is what in paired T distribution we were looking at mean square error and so on. So that is what we replace with instead of sigma squared over n. So we replace with this idea, okay. So this is my boundary confidence interval for alpha. Similarly, you can derive confidence interval for beta also. Beta is going to follow again a T distribution with this. I am not getting into the derivation, you guys can look at the derivation. I have derived it, I want you to look at it, okay. If there is any questions we can discuss, but this is what beta hat distribution is. So we have distribution for both alpha hat and beta hat or beta naught hat and beta 1 hat, okay. Both for the slope and the intercept we have the confidence limits, and it is typically based on T distribution and mean squared error. You should have guessed it, the mean square error is an estimate of sigma square, the residual, right. If mean square error is large, that is the variance is large, the confidence interval will be big or loose, and if the the variance of the noise is low or the mean square error is low, the confidence interval is going to be tight, okay. And if you have more number of data points, it will become a Z distribution, so that the confidence interval again be tighter, whereas T distribution the confidence interval will be loose if you have lesser number of data points, okay. So this is about confidence intervals of the regression problem, okay. So moving on, now we are going to talk about what is called as multivariate regression. So far we have completed univariate or single variable regression. Now we move on to multivariate regression. Again in multivariate regression all these assumptions hold good. Independence, okay. So what is the independence? Independence is the extra clause, that means what? All the multiple variables that I am using to explain the dependent variable, they are all going to be independent. So suppose if I have y equals to beta 1 x1 plus beta 2 x2 plus beta 3 x3, my usual assumption is what? x1 x2 x3 are independent and y is the dependent variable. I do not take care of relationship between x1 x2 x2 x3 and x3 x1, I assume that the relationship is 0. That is an extra assumption we make in multiple linear regression. In single linear regression it is only you single variable, you have only one variable, so no problem, only one independent, one dependent. In here I assume that if there are multiple independent variables, then they are all unrelated or they are really independent or no relationship exists between these variables. That is usually tricky, because many a times there will be relationships, and that is where you call it as feature selection. Today in modern terms, machine language terms, we call it as feature selection, because you do not want all of them to be used, because they will have relationships. Not all variables are independent variables. So you want to pick up only those variables which are independent and use them to model. Suppose if I have 100 variables, I do not care about 100 variables whether independent or dependent, I simply fit a model, what will happen? See, I have, let us say like chat GPT or you have 1 million parameters or something, right, so many to be determined. I blindly close my eyes, if you give you 10,000 data, I am trying to fit 1000 parameters. Is it good or bad? Is it good or bad? Not just computationally. What will be the issue? Suppose instead of fitting 10 independent variables, I have taken 1000 variables and fit parameters for 1000 variables, and I have used 1000 variables to explain the data, what will happen? I am saying instead of taking 10 features, I have taken 1000 features to model, what will happen? What is the issue? So what is the problem? You want to fit the data only, right? But what will happen? Why? Give me an example. What is mapping to exactly? If I use more number of parameters, what will happen? So you all know to distinguish a parrot between from other birds. How do you recognize a parrot? Color, only color. Red beak, then claws, some head features, all of those, right. Do you go, if the parrot is slightly not in green in color but it has dirt, do you fail to recognize? If the parrot's leg is broken, do you fail to recognize? If beak is damaged, do you fail to recognize? Right? You understand? So now if I build a model by doing a lot of parameters, unnecessary variables, that means they are not independent, but then all of them give the same information and then try to fit it the parrot exactly. Then how do you learn? You will learn bit by bit of parrot, pixel by pixel of the parrot. So what will happen? If a parrot becomes dirty, you will fail to recognize it is parrot, because there are too many features which you have used that are independent feature, dependent features, that gives more weightage to color. Or if you figure out that if you use too many variables that are related only to the beak, then if beak is broken, you will not recognize it as a parrot, right. So you want to build models that are usually parsimonious. Parsimonious is in limited, okay, lesser number of parameters, okay. There is a general theorem called Occam's razor, which we will not get into. So the idea is parsimonious models generalizes well. Of course there are devil's advocate to that, but still in general you do not want to fit a large model, because you know if there are features are highly interacting, it may only fit that particular training data simply because of the reason you have given weightage to a certain part, and if that is missing in the new data, it will be marked wrong, like classified wrong in the parrot case. You understand, right? We take independent features and then use it to recognize it as a parrot, right. Similarly, independence of variables is a key assumption in multiple regression. How do I choose the features? That is what feature engineering is all about. If you learn machine learning, if you say feature engineering, you are not doing anything, you are actually selecting independent variables to explain your output. That is what feature engineering is all about, okay. How do I choose variables or features that are independent, as much as independent as possible, that gives new information about the output, right. So you may look at it in frequency domain. Why? You look for frequency domain information in various frequency bands, and then in time domain you go back and look at the variance, mean, etc., kurtosis, spread, etc. That gives a complementary information. You see, these give complementary information. So if you look at features, features are usually going to be providing complementary information about the output. The reason is precisely you need as much independent variables as possible to describe your output. If you take everything to be dependent, then what happens is you will be unnecessarily biasing the system, meaning you will be overfitting for particular data that it will not gel well in the general case. Remember, I told you when I introduced learning, what do we learn? We want to learn general models from particular data, we do not want to learn particular models, then the purpose is lost, okay. So that is why this independence assumption is very important. Then we go on to normality, that assumption holds good, homoscedasticity assumption is also the same, and linearity assumption is also the same. So we are going to build a model of the form y vector equals to x vector times x matrix times theta vector, okay. So theta is, let us say, m cross 1, okay, and so there are m parameters and y is n cross 1, okay, and x is going to be n cross 1, n cross m matrix, okay, where n is your observations and m is your parameters. Is x going to be a tall matrix or a fat matrix? X is going to be a tall or a fat matrix? It is going to be tall matrix, meaning n is much greater than m. So x is a tall matrix and n is much greater than m. That means it is a, we also call it as over determined system, meaning there are more number of parameters, more number of equations compared to parameters, right. This has more equations compared to parameters. I want only, what is the unknown here? Theta, which is only m, and how many equations are there? N equations, and if n is much greater than m, so you say there are more equations, lesser number of unknowns. So that is a over determined system. The opposite is like called as under determined, where m is much greater than n, so it is a fat matrix. So example of under determined system, any example? Suppose you put a speaker here, microphone here, one microphone, 5 people talk, I want to know who talked. What happens? There is only one data, one instance. What are the unknowns? 5 unknowns if 5 people are talking. This is called blind source separation, meaning there are more separate sources, lesser number of measurements, right. So this also happens in biological problems. Both in biological problems you typically encounter both of them, over determined and under determined. Where do you get under determined in biological problems, biomedical engineering domain? Under determined. What are we trying to explain? Where do we get precise? Exactly. So if you take simple DNA base pairs, there are so many combinations possible, but will you do so many experiments? You would have possibly done with 10 or 20 people or 100 people, but the base pair combinations that could happen is in millions or even billions. So that is where, and it is an underdetermined problem. And similarly the number of combinations, the base pair combinations that could explain a particular disease is too many, and you would have done only too little experiments. Suppose you want to explain why, what is the that particular gene sequence that led to a, let us say a hereditary disease like Huntington's or fatal familial insomnia, FFI, or there are several these kind of diseases where it is familial diseases or hereditary because of particular specific gene sequences. But can I know all of them? Then I have to do billions of experiments. I may try to focus on certain pairs based on my understanding of the biology and then go after it. Typically prion based diseases, it is very hard to treat, there is no cure prion based treatments, but there are markers that will tell whether a person is vulnerable to prion or not prion. Okay. So that is a very important understanding. So if you today look at childbirth, as soon as baby is born, there are a certain kind of, even before that there is a set of you do this screening for certain base pairs. Why not do it for everything? Not possible. It is a severely underdetermined problem where m is much greater than n. We are talking about the opposite case where n is much greater than m, and this is also true in biomedical engineering where you fit models to explain efficacy, etc. There are too much data I can collect from surveys and I want to know whether it is efficient or not, the drug is efficient or not. So too little parameters, too many observations, that is also possible in biomedical. So we are talking about n greater than m instance. So how do we solve about? So the solution, if everything was unique, if everything is like I m cross m, I m cross 1 and an m cross 1, the solution would have been, what is the solution? Huh? If inverse exists, x equals to A inverse B, that is the solution, right. If x equals to A inverse B is the solution, if this would have been a straightforward case, right, but that is not unfortunately the case at all, right. So what do? I make xs square, so I pre-multiply both the sides by x transpose, okay. Then what do I have? Okay, that is a one step solution, okay. What do? I take a transpose, pre-multiply both the sides by transpose, then now x transpose x is a square matrix. What is the size of this square matrix? A transpose A is always a square matrix, you should have known by basic linear algebra. A transpose A is a square matrix always. What is the size of this matrix? M cross M, okay, which is equal to the number of parameters we want, okay, and n cross x is n cross m. What is the maximum rank of this matrix X? What is the rank of maximum rank? M, because n is not possible, n is much greater than m. So the number of independent columns is m, it cannot have independent, the maximum, assuming this matrix has m rank, x transpose x is invertible. If rank of x is m, then x transpose x is invertible, right. So then what is the theta unknown? Is given by x transpose x the whole inverse x transpose y, because x transpose x is invertible. Instead of Ax equals to b, where x equals to A inverse b, this is what is called as pseudo inverse. This is called as Pendron pseudo inverse, I will simply keep it as pseudo inverse. This is not a regular inverse, this is a pseudo inverse, clear. Yes, if the rank is less than n, you have chosen dependent features, then it is not solvable again. But nevertheless you will never have, because of uncertainties in your output, you will not exactly, none of that will go to 0, rank will never be less than m. Because of noise in the system, you will always have rank as m, because some noise will be there, so you cannot have exact dependency and therefore rank will be m. Problem is the features may be highly overlapping. Suppose 95% of the feature is overlapping, still rank will be full m, but the extra information you get by adding a new variable is only 5%, very less.
How do you measure dependent?
We will come to that, okay, we will come to that. So this is what we have done so far. We can do multiple linear regression the moment you put X as a regression matrix, okay. So the pseudo inverse gives you the solution to this problem. Now the last part I want to cover in this multiple linear regression is the question, how do I, so the R square statistic, when I talked about it, always there is a one flaw in R square. The problem is if you use more number of parameters or lesser number of parameters, the R square does not tell you anything. You could have used 100 variables, 100 parameters to explain it, still R square will be higher. Ideally if you use more number of features, the R square should come down, it should have an impact. See, suppose I fit 2 parameters to explain and 100 parameters to explain, are they both same? No, because you know that for a fact 100 parameters you may start doing overfitting. I have to somehow have a balance, right, and that is where we kind of do what is known as adjusted R square. We do not do regular R square, we do, when you look at the codes etc in your all your software codes, it will give you written adjusted R square. What is adjusted R square? It takes into account the number of independent variables used for predicting the target. So in doing so we can determine whether adding new variables to the model actually increases the model fit or not. Why are you adding a new variable, new feature, so that you can actually explain it better. Is it truly happening or not? That is what we want to know, and that is where adjusted R square helps. So adjusted R square, if you look at, you have, this is your regular R square, okay, and n is the total number of data points and k is the number of independent variables. So if k increases, what will happen? N will, adjusted R square will decrease, right, and vice versa. Okay. So every time you start adding a new variable, you should see a change in the positive change in the adjusted R square. If you see a positive significant change in the adjusted R square, that means adding that feature has helped explain your output better. If adjusted R square is not changing or it is decreasing, then you know that that feature is not. This is a very simple idea for at least for linear regression. See, it will tell you, see, the assumption of linear regression is what? It is all independent variables. Whether adding this variable to explain your output, is it useful or not? It could be such, see, if I ask you my shirt color and today's weather, they are independent variables. Can I fit a model between that? Will R square increase or decrease? That is another question. So even if it is independent, whether it adding that variable brings usefulness. If it is dependent, let us say x1 and x2 are highly dependent, x1 you used already, now if you add x2, what will happen? This will decrease because the total variability explained by x1 itself is captured and x2 is just going to add delta, and that is whether it is important or not will be told by your adjusted R square. So this adjusted R square kinds of acts as a what I call a trade off. It will tell you whether to add a new variable, new independent variable or new variable into the model or not. Okay. So that is the whole idea behind adjusted R square. Make sense? Everybody? Okay. So that sums up our linear regression and multivariate regression. I want to know whether this coefficient is significant or not. Suppose that is also another way of knowing whether this is a useful variable for explaining or not. Suppose I have 100 parameters and I know the coefficient values. If some of the coefficient values include their confidence intervals include a 0, what does it mean? Those are useless. See, simple, so this case x1 to x2, okay, your adjusted R square increased marginally, so you added. So you have y equals to beta 1 x1 plus beta 2 x2. Now beta 1 coefficient significantly outside 0. Beta 2, the confidence interval may include 0 because that is statistical. Here it is still heuristic. Why should I give n minus k minus 1 in the denominator? Basically degrees of freedom. Why would you think that it should scale linearly? Not necessary. Whereas there I give confidence intervals. There also again it is a check saying that both the coefficients should be significantly above 0. If the confidence intervals includes a 0, then I can say that this parameter is, this variable is not important to explain your output. So these are multiple checks and balances. The confidence interval is one check where you want to really see whether that particular variable is important to explain your output, like your adjusted R square. So adjusted R square may be changed by small amount, but confidence interval may include that to be a 0, then you know that this is not an important variable to be included in your model. So both confidence interval and adjusted R square can be used to determine which variables roughly I should include in the model.
So we use both these in combination.
Yes, all of this will be given as as the output of a software program. If you today do it in either Python or MATLAB or whatever R software, you will get all these values, adjusted R square value, adjusted R square, confidence intervals, all of this as parameters, and then you look at it and interpret whether these parameters are useful or not useful. which variables are to be used and which variables are not to be used. Okay. So that brings us to an end to the linear regression portion.